Assalamualaikum warahmatullahi wabarakatuh. This is Aisha Nurfaiza Nasution from 11E, and today I'll be doing my chemistry remedial. We're going to start off with paper 1. Let's look at question 1. We have Cl35 plus ion being detected in a mass spectrometer, and we need to find both its number of neutrons and its electronic configuration. First, let's get the neutrons. Chlorine's atomic number, which you can find on the periodic table, is 17. That means it has 17 protons. The mass number given to us here is 35. To find the neutrons, we just have to take the mass number and subtract the proton number. So 35 minus 17 is 18 neutrons. That immediately eliminates options A and B. Now for the electronic configuration, a neutral chlorine atom has 17 electrons. Its normal configuration would end up in 3s2 3p5. But notice the plus sign, it's a plus ion, meaning it has lost one electron. So instead of 17 electrons, it only has 16. We take that outer electron away from the p orbital, which leaves us with answer C. Moving on to question 2, we need to find the volume of a vessel containing ethene gas using the ideal equation, which is PV equals nRT. Before we plug in the numbers, we have to make sure our units are perfectly aligned with the gas constant R. So that means the pressure must be in pascals, volume will come out in cubic meters, and temperature must be in Kelvin. So for pressure, we're given 102 kilopascals. We multiply that by 1,000 to get 102,000 pascals. Temperature, we have 30 degrees Celsius. Add 273 to convert it to Kelvin, giving us 303. And moles, we have 0.56 grams of ethene. The molar mass of ethene is 2 times 12, add 4 times 1, which gives us 28 grams per mole. So moles equals 0.02 mole. So now let's rearrange the formula to solve for volume. So volume equals nRT per V, and we plug in the numbers, and then that gives us a 494 centimeter cubic. So the correct choice is B. Okay, so question 3 asks for the enthalpy change of formation of propanon, and they've given us the enthalpies of combustion. Remember the golden rule for Hess's law cycles. When you're using enthalpies of combustion, the arrows in your cycle point down towards the combustion products. Therefore, there is a formula. And now let's sum up the combustion values for those starting elements. For carbon, 3 times minus 394 equals minus 1,182 kilojoules per mole. And for hydrogen, it's 3 times minus 286, which equals to minus 888 kilojoules per mole. Oxygen is already an element in its standard state, so its combustion value is 0, and total reactant combustion enthalpy equals to minus 1,182 plus minus 188 equals minus 2,040 kilojoules per mole. Now we subtract the combustion enthalpy of our product propanon, which is minus 1,786 kilojoules per mole, and we have the answer minus 254 kilojoules per mole. That lands us exactly on C. For question 4, we need to track the change in oxidation state of titanium going from FeTiO3 to TiO2. Let's start with the product, TiO2, because it's a bit simpler. Oxygen almost has an oxidation state of minus 2. So since there are two oxygens, that's a total contribution of minus 4. Because the compound is neutral overall, the titanium must balance that out with an oxidation state of plus 4. Now let's look at the reactant FeTiO3. This is iron 2 titanate. The question itself gives us a huge hint by calling it iron 2, meaning the ion has a charge or oxidation state of plus 2. Again, we have 3 oxygens, each at minus 2, totaling minus 6. Set up a quick algebraic balance for the neutral compound, and look at that. The titanium starts with plus 4 and ends at plus 4. There's absolutely no change in its oxidation number. The answer is D. In question 5, we're asked to find an algebraic expression equivalent to the standard enthalpy of combustion of methane. Let's write out the target combustion reaction shown in the question. This time, the clues given are all enthalpies of formation. When using enthalpies of formation, the Hess's law formula is reversed. So let's look at our products. We have one CO2 which is formed, and we have two H2O molecules, so that's 2 times delta H3, and the total product is delta 2H minus plus 2 delta H3 minus. Now let's subtract our reactants. We have 1CH4 which is formed via delta H1 minus. O2 is an element, so its enthalpy of formation is 0, and the total reactants is delta H1 minus. Putting it all together and rearranging the terms slightly to match the options given to us, which matches D perfectly. Question 6 gives us a redox equation involving chlorine dioxide reacting with hydroxide ions. Let's find the oxidation number of chlorine on both sides to see what's happening. So on the reactant side, we have ClO2. The two oxygens contribute -4 total, so the chlorine atoms must have an oxidation state of +4. And on the product side, chlorine splits into two different ions. So some chlorine atoms go from +4 to +3 because they're reduced, and other chlorine atoms go from +4 to +5 because they're oxidized. This is a classic disproportionation reaction where the same element is both oxidized and reduced. Oxygen's oxidation state stays at -3 throughout. Therefore, the correct statement is C. Question 8 shows a Boltzmann distribution curve and asks what happens when you add a catalyst. Let's remember what a catalyst actually does. It provides an alternative reaction pathway with a lower activation energy. It does not alter the temperature of the gas, change the speeds of the molecules, or shift the actual shape of the curve itself. Looking at the options, B states exactly that. The number of particles with enough energy to decompose increases. That's our answer. Question 11 asks us to identify which graph correctly represents how the rates of the forward and reverse reactions change over time as the system moves towards dynamic equilibrium. When dynamic equilibrium is finally established, the forward and reverse rates become perfectly equal. On a graph of rate versus time, this means that the two curves must meet and merge into a single horizontal line. Look at our choices. Graph A shows them leveling off but remaining unequal, so incorrect. Graph B shows both rates dropping to 0. That's a completed reaction, not equilibrium. And graph C shows the forward rate starting high and dropping, the reverse rate starting at 0 and climbing, and both meeting to become perfectly equal, which is exactly what we're looking for. For question 12, we're looking for a gas, X, that causes acid rain and is actively removed from car exhaust fumes by a catalytic converter. So let's look at our choices. CO2 is a greenhouse gas, but it isn't the primary cause of environmental acid rain, nor is it removed by a catalytic converter. Carbon monoxide is toxic, but it does not cause acid rain. Hydrocarbon vapors contribute to smog, but not acid rain. Nitrogen dioxide reacts with water vapor and oxygen in the atmosphere to form nitric acid, a major component of acid rain. Catalytic converters are specifically designed to reduce nitrogen oxides back into harmless nitrogen gas. This perfectly describes nitrogen dioxide, so the answer is D. Moving on. Question 13 asks us to count the number of sigma and p bonds in the molecule HCCCH2, CH2, CHC, CH3, 2. Let's sum up our p bonds first because they're easier to spot. We have 2 from triple bond and 1 from the double bond. That's a total of 3 p bonds. This narrows our choices down to A or D. And now let's count all of the sigma bonds up. So 1 H minus C plus 1 triple bond plus 1 C, C plus 2 CH plus 1 CC plus 2 CH plus 1 C. So we have 19 sigma bonds and 3 p bonds. So the answer is D. For question 16, we need to determine which of the four structural drawings has the molecular formula C6H10O. Let's calculate the degree of unsaturation or look at the structures to help us count. The formula C6H10O has a general alkane comparison of C6H14, missing 4 hydrogens, means that the molecule must contain either 2 rings or double bonds total. So A is correct, but I'm going to tell you why B, C, and D is not correct. B, a ketone has no rings or extra double bonds. It is completely saturated apart from the carbonyl, meaning its formula would be C6H12O. Whereas C, a six-membered ring with a carbonyl and an alkene double bond, that's six carbons, but it has 3 degrees of unsaturation, meaning its formula is C6H8O. Whereas D, this is an alcohol with an alkene double bond. It has 6 carbons, but only one double bond, meaning it is C6H12O. So that's why A is our exact match. Okay, let's tackle question 17. We need to find the correct row identifying either the empirical formula or the relative molecular mass for arginine or lysine. Let's look at lysine first because it's a bit less complex visually. Let's count every atom to get its molecular formula. And now we have a C6H14 and 2O2. To find its empirical formula, we divide all the subscripts by their greatest common divisor, which is 2. That gives us an empirical formula of C3H7NO. Looking at our options table, row C suggests lysine's empirical formula is C3H7NO. That matches our derivation perfectly. So just to be absolutely sure, let's double check. It's MR equals 6 times 12 plus 14 times 1 plus 2 times 14 plus 2 times 16, which equals to 146. Row D lists the MR as 146, but it pairs with an incorrect empirical formula. So row C is completely accurate and it is our definitive choice. Okay, let's look at the free radical substitution of methane and bromine. The question says P and Q are both reactants in a propagation step and both reactants in a termination step. Let's think about the steps. In propagation, a bromine radical reacts with methane, and a later methyl radical reacts with Br2. So the radicals acting as reactants during propagation are Br and CH3. Now let's look at termination. Termination happens when any two radicals crash into each other, like Br plus CH3 equals CH3Br. Look at that, Br and CH3 are reactants here too. That perfectly fits our criteria, so B is our answer. Question 19. First, look at the functional group in the ring. We have two carbonyl groups directly bonded to other carbons within the ring. That makes it a ketone, not an aldehyde. This narrows our options down to C or D. Now let's count the total number of pi bonds. Every double bond contains exactly one pi bond. Inside the main ring, we have two C double bonds, CO double bonds, and two CC double bonds, which gives us a 4 pi bonds right there. Then look at the repeating unit in the brackets. There is one C double bond inside it. Inside it repeats n times. That gives us n more pi bonds. Add them together and you get n plus 4. Therefore, the correct row is D. For question 20, we need to find the option that correctly represents the three structural isomers of pentane: unbranched pentane, isopentane, and neopentane. Let's look at option A. The first formula is a straight 5-carbon chain. The second has a 4-carbon chain with a methyl group on the second carbon. The third is a central carbon bonded to 4 methyl groups. These are exactly the three distinct structural isomers. If you look at B, the second and third formulas are actually the exact same molecule, just written differently. C and D have incorrect or repeating skeletal drawings, so A is the correct answer. Question 21. When you hydrolyze an ester using an acid, it splits right at the CO single bond next to carbonyl group. The carbonyl CO double bond side gains an -OH group to turn back into carboxylic acid. Let's split X to X. The carbonyl side has two carbons, CH3 C double bond O, so it forms ethanoic acid, CH3COOH. Now let's split S to Y. Find the C double bond O. The alkyl chain attached to that carbonyl has 3 carbons in a straight line. That means it forms propanoic acid, which is CH3CH2COOH. Matching these up with our table, option A is the correct combination. Question 22. We're looking for a reaction where the organic starting material gets oxidized. Let's check A. We start with an aldehyde, CH3CH2CH2CHO, and treat it with Tollens reagent. Tollens reagent is a mild oxidizing agent that oxidizes aldehydes into carboxylic acids while reducing silver ions to a shiny silver mirror. This is a textbook oxidation reaction. The other options: B is a reduction using LiAlH4, C is a dehydration, and D is ester hydrolysis. None of these are oxidization, so A is definitely the right answer. Question 23. An addition reaction across an alkene double bond C double bond C means the two incoming air atoms must attach to the adjacent carbon atoms that originally shared the double bond. If we react a butene isomer with the bromine, then the two bromine atoms must end up on neighboring carbons like positions 1 and 2. This forms 1,2 dibromobutane. You can't get 1,1 or 1,3 dibromobutane from a simple electrophilic addition because the halogens can't jump to non-adjacent positions or stack on the same carbon in one step. This makes B as our correct choice. Moving on to question 24. We need to tell propan 1-ol and propan 2-ol apart. Options A and B won't work because acidified KMnO4 and K2Cr2O7 will oxidize both of them, changing color in both test tubes. No distinct difference there. C is dehydration, which yields similar alkenes that both decolorize bromine water. Now look at D. Mild oxidation turns the primary alcohol into an aldehyde and the secondary alcohol into a ketone. If we then add Felling's reagent, it will react with the aldehyde, giving a red precipitate, but do absolutely nothing to the ketone. That's a perfect visual distinction, so D is correct. Okay, question 25, geometric isomers and reduction. Let's look at the structures. In molecule X, both carboxylic acid groups are on the same side of the C-C double bond, which makes the X the cis isomer. This eliminates C and D. Now, what happens when we reduce them? Reducing the C-C double bond turns it into a C-C single bond, which allows for free rotation, because the molecule becomes a symmetrical saturated dicarboxylic acid. Any difference created by the original spatial arrangement disappears. Since the resulting chains can freely rotate to match each other perfectly, compound P and compound Q are completely identical. That leads us straight to A. When 2-methylpentene reacts with HBr, we use Markovnikov's rule to find the major product. The hydrogen atom attaches to the double-bonded carbon that already has more hydrogens, while the bromine attaches to the more substituted carbon. Let's look at the double bond between carbon 2 and carbon 3. Carbon 2 is bonded to two methyl groups. Carbon 3 is bonded to a hydrogen and an ethyl group. According to the rule, the H goes to carbon 3 and the Br goes to the more substituted carbon 2. This forms 2-bromine-2-methylpentane. But wait, let's double check our options. Let's draw the carbocation stability instead to be absolutely sure. Carbon 2 creates a tertiary carbocation which is highly stable, so the Br minus attacks carbon 2. This gives us 2-bromine-2-methylpentane, which corresponds to option B. Question 32. A chiral center is a carbon atom bonded to four entirely different groups. Let's scan this symmetrical disodium chromoglycate molecule. The large aromatic ring structures on the left and right are completely identical. If you look closely at the central linker chain, there is a carbon in the very middle holding an OH group and a hydrogen atom. What else is it bonded to? To its left, it is bonded to a CH2O ring group, so its right it is bonded to an identical C2O ring group. Wait, because the left and right groups are identical, the central carbon only has three unique groups, meaning it isn't chiral. Let's look closer at the diagram to see if there's an asymmetry. Looking closely at the central carbon, it's connected to CH2O ring on both sides. Because of the perfect symmetry of the molecule, there are actually zero chiral centers. The answer is A. Moving on, we have two clues for compound X. First, 1 mole of X reacts with 8.5 mole of O2. We can use the general combustion formula to find out how many carbons and hydrogens it has. Second, X does not react with acidified KMnO4. This tells us X must be a tertiary alcohol or a ketone because primary and secondary alcohols oxidize easily. So let's test the combustion of molecule 3. The oxygen balance works perfectly perfectly. 6 times 2 plus 7 equals 19. Oxygen's on the right. 1 plus 8.5 times 2 equals 19 on the left. Molecule 2, C6H12O, would need 8 mole of O2. Therefore, only molecule 3 fits both clues perfectly. The answer is C. Question 34. To name the reagents used to build ester Z, let's break it down at the single CO ester bond. The part containing the carbonyl carbon C double bond O comes from carboxylic acid. Counting the carbons in that chain, we see 4 carbons in a row, which means our starting acid is butanoic acid. The part attached to the single bond oxygen comes from the alcohol. It is a 3-carbon chain, but notice the oxygen attaches to the middle carbon. That means the alcohol used is propan 2-ol. Putting these together, row C gives us the perfect match. Let's take a look at this IR spectrum on question number 37. The absolute dead giveaway here is that the massive ultra-broad absorption peak stretching all the way from 2500 to 3300. That shape is characteristic of an OH stretch in carboxylic acid. Right next to it, sharp and strong around 1720, we see a distinct CO double bond carbonyl stretch. A molecule with both a carboxylic acid OH stretch and a C double bond O stretch must be a carboxylic acid. Looking at our choices, propanoic acid fits this description flawlessly, making C our correct answer. Okay, 39. This question gives us 2 clear signals, a broad peak at 3000 and a strong peak at 1710. Just like before, a very broad peak centered around 3000 indicates an OH group belonging to a carboxylic acid, while the peak at 1710 tells us there is a C double bond O carbonyl group present. Combining these clue points directly to a carboxylic acid functional group. Scanning our options, propanoic acid is the only carboxylic acid listed. Thus, the answer is C. Alright, our last question, number 40. We have a compound with an empirical formula C2H4O. Let's inspect the IR spectrum first. There is a strong sharp peak near 1740, which tells us that a C double bond O bond is present. Notably, there is no broad OH peak anywhere above 3200, so we can eliminate options C and D right away since they contain alcohol groups. That leaves us with option A, an ester, and option B, a cyclic ester or lactone. Let's check the molecular formulas to match our empirical ratio. Option A has 4 carbons, 8 hydrogens, and 2 oxygens. Simplifying this gives an empirical formula of C2H4O. Option B has 4 carbons, 6 hydrogens, and 2 oxygens, which simplifies to C2H3O. Since option A matches our empirical formula perfectly, A is the correct answer. Now that paper 1 is done, let's move on to paper 2. Alright, question 1. Here we have 3 halogens and we have to complete the table, which is its color at 293 Kelvin. So, chlorine is yellow, bromine is red, and iodine should be gray-black. For 1b, the trend in volatility, it decreases down the group. So as we go down group 17, the halogen molecules get darker and contain more electrons. This increases the strength of London dispersion forces between molecules. More energy is needed to separate the molecules, so they evaporate less easily and become less volatile. Now for 1e, atomic radius trend, across period 3 the number of protons increases but electrons are added to the same energy level. Shielding stays almost constant, so nuclear attraction increases. The outer electrons are pulled closer to the nucleus, causing atomic radius to decrease. So for 2a, CaO2 plus H2O should be CaOH2. Why? Because calcium oxide is a basic oxide, so when a metal oxide reacts with water, it forms a metal hydroxide, not a hydride. For 2b, down group 2, the metal ions become larger, so the distance between positive and negative ions increases, reducing electrostatic attraction. Weaker ionic bonding means less energy is needed to melt the oxide. So 2c, why strong heating is needed? It's because it's to overcome metallic bonding. So group 2 metals contain strong metallic bonds between positive metal ions and delocalized electrons. A large amount of energy is needed to break these attractions before the metal can react with oxygen. Now 2d. bond angle in BeCl2? So the answer is 180 degrees because beryllium forms two bonding pairs and has no lone pairs around the central atom. According to electron pair repulsion theory, the bonding pairs arrange themselves as far apart as possible, giving a linear shape with a bond angle of 180 degrees. For 2EI, the forward and reverse reactions occur at the same rate. Why? Because both reactions continue simultaneously, but neither reaction causes any overall change in concentration. So for 2EII, I write first the expression for Kp. Since only gases are included, solids are ignored. That gives me Kp equals to PO2 per PCl2 squared. Next, the question says that 70% of the chlorine reacted. If I assume I started with 100 moles of chlorine, then 70 moles react, leaving 30 moles. According to the equation, every 2 moles of chlorine produce 1 mole of oxygen, so 70 moles of chlorine produces 35 moles of oxygen. At equilibrium, there are 30 moles of chlorine and 35 moles of oxygen, giving a total of 65 moles of gas. I then use mole fraction times total pressure to find the partial pressures. Finally, I substitute these values into the Kp expression and obtain 2.5 times 10 to the power of minus 5 Pa power of minus 1. 2Fi. The peroxide ion has an overall charge of minus 2. Since there are two oxygen atoms, they share the charge equally. Therefore, each oxygen has an oxidation number of minus 1. 2F2, enthalpy change of formation. The enthalpy change when 1 mole of a compound is formed from its constituent elements in the standard states under standard conditions. 3A, covalent bond, a strong electrostatic attraction between a shared pair of electrons and the nuclei of the bonded atoms. So the shared electrons are attached to both nuclei simultaneously, holding the atoms together. 3B, sigma bond. A sigma bond forms an end-on overlap of orbitals along the line joining the nuclei. Pi bonds form by sideways overlap of parallel p orbitals above and below the plane of the molecule. So the sigma bond is stronger because the overlap is greater. 3BIII. So the major product is 2-bromopropane. So the pi bond contains a high electron density and attacks H plus from HBr. The more stable secondary carbocation forms, which is then attacked by Br minus. This follows Markov-Nikov's rule and gives 2-bromopropane as the major product. So for 3C, 3C is C3H6, so the sigma bond is 8 and pi is 1. So every single bond is a sigma bond. The double bond contains one sigma bond and one pi bond. C3H7OH, there is 11 sigma bonds and 0 pi bonds. So there are only single bonds in the alcohol, so all bonds are sigma bonds. For 3EII, significance of area B. So area B represents the proportion of molecules with energy greater than or equal to the activation energy after adding the catalyst. Since more molecules have sufficient energy to react, there are more successful collisions per second and the reaction rate increases. Now 3F, functional group in Z, aldehyde only, because Toland's reagent gives a silver mirror only with aldehydes. Since Z was distilled off immediately, further oxidation to a carboxylic acid was prevented. This last sentence is exactly the kind of explanation we need. For the table in 3GI, A is but 1-ene, B is cis but 2-ene, C is trans but 2-ene, D is 2-methylpropene. Lastly, stereoisomerism, compounds that have the same structural formula but a different arrangement of atoms in space. So, the atoms are connected in the same order, but their three-dimensional arrangement is different, giving different stereoisomers such as cis-trans isomers. That is all for paper 1 and paper 2. Thank you. Assalamualaikum warahmatullahi wabarakatuh.